Hi, this is Professor Bennett from digitalaudiotheory.com. This programming example comes from Chapter 8, which covers FIR filters. Now, convolution is an algorithmic way of processing a signal through an FIR filter. One typical use of an FIR filter structure is to load up the coefficients with the values of an impulse response, or IR. An IR can be captured from anything: a room, a microphone, a cabinet. An IR captures the character of an audio system or device, and processing a signal through an IR using convolution imbues that signal with the character of the audio system or device that the IR was captured from. In this programming example, you will record your own voice and convolve it with an IR that can be downloaded from digitalaudiotheory.com, or simply use any IR that you have at your disposal. We're going to use two functions here, audio recorder and record blocking. So this sets up the properties of our audio recorder. It's going to be mono, 16-bit, 44.1. Then record blocking stops all other processing on MATLAB and allows the audio to be recorded for this amount of time right here in seconds. So we're going to record 2 seconds of audio, and then we can pull out the audio using get audio data. If you're on Octave, you'll use this function instead. Digital audio theory. And then we can audition the recording using the play function. Now notice we're using play on R, digital audio theory, but we could also use a function such as sound_sc by passing also the sampling rate on X. Digital audio theory. All right. So next we need to load in the IR. Here we have it. In fact, if you want to listen to this too, we can. There we go. Hopefully you can hear that. And we already know the length of our output. The output of the vocal recording being convolved with the IR will be the sum of their individual lengths minus one sample. So we can go ahead and create an output Y that is full of zeros of the correct length. Okay, here is our convolution algorithm. So we're writing this from scratch by implementing the convolution algorithm from the textbook. So this comprises 2 nested for loops. The outer loop iterates over N. In a real-time digital audio system, N is the current sample index. The inner for loop must be computed in its entirety. This must be computed in its entirety to produce a single sample, output sample, Y of N. So every time that N increments here, the input signal X is shifted one sample further into the filter, into the FIR filter. And the inner for loop here is an accumulation. You see it here. You see the output Y equals whatever the output Y was plus something else. That's how you write an accumulator. It accumulates all the interactions between the portions of the input signal, the shifted input signal, that are inside the filter and interacting with the coefficients of the filter. So every sample of X gets multiplied by its corresponding coefficient. Then those products are all summed together to produce a singular output. This process repeats for each and every shift amount until X, our input, is fully passed into and then out of the filter. We can audition our recording both with and without IR filtering. In the next programming examples, we'll take a look at 2 uses of correlation, a very similar process to convolution. So let's run this. You see it's going to take a hot second here. There we go. And let's listen to the output. Digital audio theory. Let's listen to the dry version again. Digital audio theory. And convolved with the IR. Digital audio theory. Now MATLAB also has a built-in command for convolution called conv, and you just pass it the two signals. So let's run this. Now notice the length of y2 should be the same as the length of y. Good. And let's listen to its output. It should sound just like y. Digital audio theory. Digital audio theory. Well, there you have it. Thanks for watching.